All right, we're going to look at some examples on Study Island of compound probability just to work out some of these together, just in case you're looking for more examples. In this case here, an experiment is broken up into two parts. The first part of the experiment of a penny is tossed in the air. If the coin lands on heads, then the coin is flipped a second time. If the coin lands on tails, then the six-sided die is rolled. What's the probability of getting a head and a 5? So I want probability of heads and probability of a 5. All right? And this keyword "and," just a reminder, "and" tells me that I'm going to multiply these two results here. So first off, probability of getting a head. If I flip a coin, that is one out of the two possibilities. And don't jump too quickly to finding the probability of 5 going 1/6 and then multiplying these. You're going to get that wrong. Because look at what happens. If the coin lands on heads, what's the result? Well, then the coin is flipped a second time. That means that if the coin lands on heads, which is what we're looking for, are we even going to roll a die? No, we're not even going to roll a die. We're going to be flipping another coin, which means the probability of getting a 5, if we got heads the first time, is actually 0. All right? Because there's no chance you'll get a 5 if you get heads, because you won't be rolling a coin. You won't be rolling a die. So in this case, 1/2 times 0 is 0, making 0 our answer. Mark has a standard deck of 52 cards and a fair two-sided coin. Fair means that it's not weighted and both sides could land evenly. That's what fair means. You'll typically be doing probability with fair die and fair coins. What's the probability that he will pull a jack from a deck of cards and toss the coin to land on heads? Now, this does require that you know something about a deck of cards. A deck of cards has diamonds, it has hearts, it has clubs. That's a bad club. And it has a spade. All right? So there's a jack in each one of these. So that means in a deck of 52 cards, there are 4 jacks. All right? So you could see when we're looking at the probability of getting a jack, we can see that that's 4 out of 52. Now, if you're really good, whoops, that is not a 2. All right? If you're really good about a deck of cards, all right, you know that not only is it 4 out of 52, but every suit has 13 cards in a suit. So the jack is one of those 13 cards. So this does reduce down to 1/13. All right? Now we want the probability of jack and the probability that the coin will land on heads. Well, and means multiply. Heads is 1/2. And therefore we can multiply these two together. 1 times 1 is 1. And 13 times 2 is 26, giving us 1/26 for our compound probability there. All right, in this one, Chris has a bag of 4 apples. 3 of the apples are red and 1 of them is green. He also has a bag of 2 sandwiches. One of the sandwiches is ham and the other is turkey. If he reaches into both bags without looking, what's the probability that he will grab a red apple? So probability red and probability of turkey. All right? Well, if that's the case, probability of red and turkey, let's look at the probability of each. There were 3 of the apples that are red, so 3 red out of the 4 total apples. And the probability of turkey was 1 out of the 2 sandwiches. And if we multiply those together, because I want both of them to happen, 3 times 1 is 3, 4 times 2 is 8, giving me a probability of 3/8. Kayla has a standard deck of 52 cards and a 6-sided die. What is the probability that she will pull a diamond from the deck of cards and roll a 5? Well, again, just to give you a refresher, that diamond is 1 out of the 4 suits of hearts, clubs, diamonds, and spades. So it is 1 out of the 4 possibilities. So the probability of a diamond is 1/4, and telling me to multiply. Rolling a 5, probability of 5 is 1 out of 6 options. If we multiply those two together, we get 1 out of 24 as our probability. All right, in this case here, Harold has 1 bag of different colored, same size chips and 1 bag of different colored, same size marbles. In the first bag, there are 4 blue chips. Let me just get this in. 4 blue chips, 5 red chips, and 3 black chips. That is a total of 12 chips altogether. In the second bag, there are 5 green marbles plus 4 blue marbles plus 3 red marbles, giving me a total of 12 marbles altogether. All right, we want to know what's the probability that we will pull a blue chip and the probability of a blue marble. Well, again, what's the probability of a blue chip? The blue chips were 4 out of these 12, in other words, 1/3 of the bag. And probability of a blue marble, well, there were 4 blue marbles. Hey, another 4. So 4 out of 12, another 1/3. And 1/3 times 1/3 is 1/9. My probability I'm looking for here is 1/9. All right, and this one here. In an experiment, a 6-sided die is rolled a number of times. The results are shown below. The number rolled, the number of times rolled, and it shows you. Based on these results, what is the experimental probability of rolling either a 4 or 5? Experimental probability means the actual results that happened, not theoretically what should happen. Theoretically, if you roll a 6-sided die, it should be 1/6 for every single one. Every 6 rolls, you should get all 6 numbers. That would be the theoretical experiment, the theoretical probability. Experimental is actually what happened. So we want either a 4 or, hey, we're getting the keyword or here, a 5. Remember, that keyword or tells us to add the results. So probability of a 4, well, we had a total of, let's find our 4s, that is 3. That was 3 out of the, how many times it was rolled? Well, if we look at this, 3 plus, let me add them all up. 3 plus 7 is 10, plus 4 is 14, plus another 3 is 17. 17 plus 5 is 22, plus another 9 gives me 31. So 31 possibilities here. All right, so 3 out of those 31 were 4s. All right, that's this one right here. Or, tells me to add 5. How many 5s did we get? Well, 5 was 5, actually. We had 5 rolls, 5 5s rolled. All right, and that's 5 out of 31. So that gives me a total. If I add these together, remember, in adding fractions, we keep that denominator, add the tops. 5 plus 3 is 8, giving me 8 out of 31 as my experimental probability in this case. We've got another experimental probability one here. If you just watched the last one, maybe pause the video. Try to do this one before we continue. If you're coming back in now, remember, experimental probability is what actually happened. So in this case, we want the probability of a 3 or the probability of a 4. All right, in this case, probability of a 3. Well, let's check out how many 3s there were. There were 3 out of a total of 33. If we are to add all of these up, there were 33 rolls that happened. All right, or it tells me to add probability of a 4. There were 9 4s. That's 9 out of the 33 rolls gave me a 4. Well, adding them, remember, add the tops. 9 plus 3 is 12, and keep the denominator when we're adding those, giving me 12 out of 33. That can be reduced because 3 goes into both of those. 3 goes into that 4 times, and 3 goes into that 11 times, reducing this fraction down to 4/11ths as my probability. All right, let's take a look at our last one here. A parking lot has 66 parking spaces numbered 1 to 66. There are no cars in the parking lot when Jillian pulls in and randomly parks. What is the probability that the number on the parking space where she parks is greater than or equal to 21? Now, this seems like a pretty simple, straightforward, because it's not really compound probability, but there is a little bit of a snag to this if you don't pay attention. First off, 66 spaces. We know that it's going to be out of 66, but how many of those are greater than or equal to 21? Well, if we look at it and we count 1, 2, 3, and so on up to 20, and then 21, all right, and then so on up to 66, okay? When we look at this and we say how many are greater than or equal to 21, you might be tempted to just subtract 21 at first, but you're not looking to subtract 21. You're only looking to subtract 20. 20 of the spaces will be less than 21. All right, so be careful there. And if I subtract 20 from that, we actually get ourselves 46 of the possibilities that remain. And if we reduce ourselves 46 over 66, that does reduce down to 23 over 33, which would be our answer in this case. So just be careful there. All right, I hope that's enough. If you have more questions about compound probability, come see me in class.